central limit theorem describes the relationship between a population and a sample. A population is the entire group or collection that we wish to study. A sample is a subset, randomly selected, of the population, used to get an indication of the parameters of the population. For the purpose of illustration, we will start with a small population of 5. This very simple population has 5 items, and the mean of these values is calculated using this equation. It is the sum of these values divided by the number of values in the population. The numerator is 15, the denominator is 5, making the mean of the population equal to 3. Recall the equation to calculate the standard deviation. We introduced it in the video on measures of center and spread. Please review it if you feel you need to. Once calculated, the standard deviation is 1.4121. We will now take samples of our population. Each sample will have a size of 2. Our first sample will have the values of 1 and 2 taken from the population. To calculate the sample mean, we do the same as we did to calculate the population mean, except now we sum the values in the sample to get 3, then divide by the sample size of 2 for a result of 1.5 for the mean of the first sample. The mean of a sample is designated by an X with a bar over the top and is read as X bar. The next sample consists of the values of 1 and 3 taken from the population. As we did for the last sample, we add 1 and 3 to get 4, then divide by 2 the sample size to get a value of 2.0 for the mean of the second sample. We continue this process until we have every combination of the 5 members of the population, calculating the mean of each sample as we go. Recall the equation for calculating the number of combination of n objects taken k at a time. In our case, the n objects would be the 5 members of the population, and the number taken at a time is the sample size of 2. When we evaluate this equation for 5 objects, taken 2 at a time, we get 10 possible combinations. This is the number of samples we have, assuring us that we have all the combinations. In summary, we have the means of all the samples of size 2. This can now be thought of as a distribution with its own mean and standard deviation, and we'll now refer to it as the sampling distribution. The equation for the mean of the sampling distribution is similar to the one for the mean of a single sample, but is different in 2 important respects. The first is, in the numerator, for the sample mean, it is the sum of the members of one sample, while for the sampling distribution, the numerator is the sum of the means of all the samples. The denominator for the sample mean is the sample size, and for the sampling distribution, the denominator is the size of the sample population. The Greek letter mu is used to represent the mean of the sampling distribution, with the subscript x bar to distinguish it from the mean of the population. This is also a mean of a population, but it is a population of samples. Let's now calculate the mean of our sampling distribution. The sum of all the means of the sampling distribution is 30, and the number of samples in this distribution is 10. This makes the mean of our sampling distribution equal to 3. Let's not forget that the mean of the population from which the samples were taken is also 3. The standard deviation of the sampling distribution is given by this equation. The sampling distribution mean is what we just calculated, and the denominator inside the radical is the number of samples in the sampling population, which is 10 for this example. The x bar is the mean of the individual samples. If you need to review how to calculate the standard deviation, please review the video on measures of center and spread. The result is that the standard deviation of the sampling distribution is 0.8660. Note that this value of the standard deviation for the sampling distribution is less than the standard deviation of the population from which the samples were taken. We will be discussing why this is the case momentarily. Let's do the same for a sampling distribution from the same population of 5 values, but with a sample size of 3, resulting in a new sampling distribution. Using the same equations, we next calculate the mean and standard deviation of the new sampling distribution and get these results. Note that the sampling mean is once again equal to the population mean. In general, the mean of the sampling distribution is equal to the mean of the population. The standard deviation of the sampling distribution is less than the standard deviation of the population, and is also less than the standard deviation of the sampling distribution that has a sample size of 2. The fact that the standard deviation of the sampling distribution gets smaller for large sample sizes is a crucial element of the central limit theorem. An alternate equation for the standard deviation of the sampling distribution is this one. For this equation, we must know the standard deviation of the population, the size of the samples, and the size of the population. Let's now calculate the standard deviations of our sampling distributions and see if we get the same results. We'll start with the sampling distribution of samples of size 2. For the standard deviation of the population, we use the value calculated earlier. For lowercase n, we use the sample size. For uppercase N, we use the population of size 5. Finally, the 1 is just a constant from the equation. When we carry out the calculation, we get 0.8660, which is the same result calculated with the other equation. Let's now use the equation to calculate the standard deviation of the sampling distribution where the sample size is 3. All the variables have the same value as the previous example, except for the sample size, which is now 3. Completing the calculation results in the value of 0.5774, which is the same value we calculated with the other equation. What we want to remember from all this is the relationship between the population and a sample of the population reduces to these two equations. The mean of a sampling distribution is equal to the mean of the population, and the standard deviation of the sampling distribution is a function of the standard deviation of the population and the size of the sample and the size of the population. The real value of the central limit theorem is not evaluating small populations like we just did for illustration's sake, but for cases where the population is very large and the sample size is quite small in comparison. This means when n is very large and n is small in comparison, this portion of the equation approaches 1, meaning the standard deviation of the sampling distribution is equal to the standard deviation of the population divided by the square root of the sample size. These two equations are the essence of the central limit theorem. The value of these equations is not what we can say about the sampling distribution for a given population, but it is what we can infer about a large population from a small sample. We will discuss these possibilities in great detail in later videos. First, let's examine the relationship of the population to the sampling distribution graphically. Let's look at a population distribution with a mean equal to 80 and a standard deviation of 30. This is the graph of this distribution with a dashed line indicating the location of the mean. A sampling distribution from this population distribution with a sample size of 2 has this graph. Its mean coincides with the mean of the population because the mean of the sampling distribution is equal to the mean of the population, and therefore has the same value as the population mean and is equal to 80. The standard deviation of the sampling distribution is the standard deviation of the population divided by the square root of n. The standard deviation of the sampling distribution is 30 divided by the square root of 2 for a result of 21.21. If the sample sizes were to be larger, the shape of the sampling distribution changes because the value of the standard deviation is becoming smaller. Let's leave n equal to 9 for the next illustration. The shaded area under the population distribution extends from 55 to 65, and its area is equal to the probability of x, the random variable, falling between the values of 55 and 65. Using the method described in the video on the standard normal distribution, we determine the probability to be 0.1062. The area under the sampling distribution between 55 and 65 is visually smaller, and is equal to the probability of x bar being between 55 and 65, and is equal to 0.0606. Remember what the difference between these two probabilities is. Here we have the probability of a random variable of the population being between the values of 55 and 65, while here we have the probability of a mean of a random sample of size 9 being between the values of 55 and 65. As the interval moves to the right, both probabilities increase, but the probability of x bar is increasing faster. When the interval straddles the mean, we can see that the area under the sampling distribution is greater than the area under the population distribution. This property can be illustrated further by increasing the sample size. It is this property of the sampling distribution that makes the central limit theorem important. That is, as the sample size increases, the mean of the sample becomes a better estimate of the population mean. We will learn how to make use of this property in later videos.